You know, when you watch a robotic arm, like gracefully snap a tiny microchip into place, it looks like this solid block of metal just executing flawless code.
Right, that's the core illusion of robotics.
Yeah,
We just expect steel to be completely unyielding.
exactly. But looking through this technical slide deck on harmonic drives we're deep diving into today, you realize that perfect motion is actually this constant, invisible war against physics. I mean, that metal isn't perfectly rigid at all. It wiggles, it bends, and it fights back.
Yeah, a harmonic drive is actually highly flexible by design, which is kind of wild to think about when you need sub-millimeter precision.
So let's use the classic diving board analogy here. You jump on it and it bounces. Literally every mechanical system has a resonant frequency, right? Like that specific pitch where it hits maximum amplitude.
Yes, and because harmonic reducers are built to flex, their resonant frequency is notoriously low, which is a major headache.
Wait, why is a low frequency worse?
Because that low frequency interferes directly with the servo motor's control loop. It creates this runaway instability. And, I mean, you can't just ask the metal to stop obeying physics.
Right, so you have to fix it in the software. You tune the servo controller's notch filter to, selectively mute that specific chaotic frequency.
Exactly. The software ignores the frequency, but the physical metal is actually still vibrating slightly when the arm reaches its target coordinates.
Ah, so you're forced to wait for it to stop micro-shaking before it can actually do its job.
Right. Engineers call that settling time. If your reducer has lower rigidity, meaning it's inherently more bendy, you're looking at a longer wait.
Which is terrible for throughput, right? In high-speed pick-and-place manufacturing, waiting even a fraction of a second completely destroys your efficiency.
Absolutely. The physical solution there is improving the reducer's torsional stiffness. But even if you solve the stopping and settling, you still have to deal with the forces fighting the robot while it's actually in motion.
Right, the dynamic friction, the internal rotational resistance that fluctuates constantly based on velocity and gear temperature.
Yeah, and that shifting drag unpredictably drains the motor's current. So engineers measure the friction across varying speeds and build feed-forward compensation into the motion control algorithm.
So the software essentially predicts the mechanical resistance before it happens and preemptively spikes the power.
You got it. It's a constant predictive balancing act.
Okay, but here's where I need to push back on the pure math of that control algorithm. Doesn't the sheer mass of the payload completely warp those calculations?
Oh, entirely.
I mean, an empty gripper moving through space is completely different from one slinging around a heavy car door,
It
right?
completely changes the system dynamics.
Yeah.
You are constantly balancing the load's inertia against the internal inertia of the motor and reducer, which brings us to the moment of inertia ratio.
Right, the sources specify keeping that ratio below 5:1.
Exactly. If it exceeds that threshold, the control loop just can't compensate for the external mass.
And you get runaway oscillation.
Yeah, it tears the control stability apart. Keeping that inertia ratio tightly controlled under that 5:1 limit is what keeps rapid acceleration mathematically stable.
Okay, so we have the notch filters running, the inertia ratio mathematically locked in, but in a real-world manufacturing environment, unexpected dynamic shocks happen. Someone hits the panic button, right?
Yeah, E-stop is triggered. And that massive amount of kinetic energy from a high-speed arm suddenly frees, well, it has to go somewhere.
This is where overload capacity comes in. The maximum torque the reducer can handle short-term without permanently shearing or, stipping teeth.
Right. During an E-stop, a harmonic reducer can actually withstand impact torques up to 300% of its rated value.
Wait, 300%. That is a massive spike. And here is the brilliant full-circle design insight from the slide deck.
I think I know where you're going with this.
The very reason it can absorb a shockwave 3 times its normal limit without shattering is because of that flexibility we talked about earlier.
Exactly. The low rigidity that caused us so much headache with resonant frequency is the exact same property that allows the gears to flex.
They absorb a massive impact rather than breaking like brittle glass. It's just a phenomenal engineering trade-off.
It really is. The inherent weakness in precision control becomes its ultimate survival mechanism during a catastrophic event.
So behind every incredibly smooth automated movement are these violently battling forces of friction, inertia, and resonance. It's a delicate mastery of physical limits.
Yeah, you're not just watching code execute. You're watching mechanical energy being continuously captured, filtered, and redirected.
So next time you watch a robotic arm gracefully assemble a fragile smartphone component, ask yourself, are you really marveling at the genius of the software, or are you actually witnessing perfectly balanced mechanical limits hiding just beneath the metal?
It's always both, really.
For sure. And, if software can mask physical flaws so well, what happens when we start designing materials that can dynamically change their own stiffness on the fly?
Yeah.
That's something to think about.